Welcome, curious minds, to another deep dive. Today, we're pulling back the curtain on something really fundamental. It's at the heart of pretty much all the tech you use every day. We're talking about the chips, the brains inside our devices. Now, you know they're incredibly complex, right? But maybe you've wondered what really goes on inside them, what makes them work so well, or, sometimes glitch out. So, we're going deep into VLSI, very large scale integration design. And we're focusing on two maybe slightly intimidating terms, skew and slack.
Mhm.
They might sound super technical, and well, they are, but understanding them is actually key to knowing why your phone streams video smoothly, or why sometimes it just doesn't. Our mission today, to unpack these ideas, maybe use some helpful examples, and really get why they matter so much for making our digital world, well, work. So let's unpack this. When we talk about a clock in a microchip, it's definitely not the kind you hang on a wall, right? It's more like a
Mm.
heartbeat, a rhythm. What exactly is clock skew in these super intricate circuits?
That's a perfect analogy, actually. The clock signal is the heartbeat. Imagine billions, literally billions, of tiny components inside that chip. They all need to work together, perfectly synchronized. The clock is this regular pulse sent out from a central source. It tells all the synchronous bits, like flip-flops, think of them as tiny memory cells, exactly when to grab and process data. Now, clock skew. That's the phenomenon where this clock signal, this heartbeat, doesn't quite arrive at all those different parts at the exact same instant.
Ah, okay. So it's not perfectly simultaneous everywhere.
Exactly. There are tiny delays.
So kind of like a big marching band where maybe the people further from the drummer hear the beat just a fraction of a second later. Could you give us a really concrete example? Make it a bit less abstract.
Sure, absolutely. Let's picture two flip-flops. We can call them A and B. They're connected, so data flows from A to B. Now, both of them need that clock signal to know when to operate. But because of the actual physical distance, the signal travels, even though it's microscopic. And maybe tiny differences in the wires, the interconnects we call them, or the gates.
Mm.
The clock might hit flip-flop A at time t, but it might reach flip-flop B just a tiny bit later, say at time p plus n.
Mm-hmm.
That little difference, and could be picoseconds, maybe nanoseconds, that is your clock skew. It's just a consequence of physics sending signals across a complex surface.
Right, I see. So the actual layout matters, how long those tiny wires are, maybe even what they're made of. It's fighting these tiny, tiny differences. Wow. Okay, that sounds like it could be chaos across a whole chip. Do designers, categorize this skew somehow to try and manage it?
Oh, definitely. It's not chaos. Oh, well, the goal is to prevent chaos. Managing it is crucial. We do categorize it mainly into two types. First, there's local skew. This is specifically the timing difference between clock signals arriving at flip-flops that are directly connected, like our A and B example. Super important for clean data transfer between stages.
Okay, directly connected ones.
Right. And then there's global skew. This looks at the timing difference between any two flip-flops on the chip, whether they're directly linked or on opposite sides. Global skew is more about the overall synchronization of the whole system. Local skew is about specific data handoffs. You have to control both very carefully.
That's interesting. So local versus the whole chip picture. Okay, so this difference, this and the skew, does the direction it goes matter? Like if the clock arrives later at the second flip-flop versus earlier,
Yeah.
can skew sometimes be good? Or is it always bad news? That's a really sharp question. And yes, the direction matters immensely. Skews can be positive or negative, and it makes a huge difference to the circuit's timing. It all comes down to how the clock arrives relative to the data signal that needs to be captured. And this brings in two absolutely critical ideas: setup time and hold time.
Ah, set up and hold. Heard of those. Can you give us a quick refresher?
Sure. So imagine data arriving at a flip-flop. It needs to be stable before the clock edge arrives to capture it cleanly. That minimum time, it needs to be stable beforehand. That's setup time.
Okay, stable before the clock hits, like getting ready for a photo.
Exactly. If it's not ready early enough, you get a setup time violation. The wrong data might get captured. It's unreliable. Then there's hold time. This is the minimum time the data must stay stable after the clock edge has arrived.
She's stable after two.
Right. Can't change too quickly right after the clock edge. If it does, that's a hold time violation. Again, leads to errors. Data capture gets messed up.
Got it. Set up before, hold after. So
Mhm.
how does skew play into these?
Okay, let's connect it. Positive skew happens when the clock arrives later at the destination flip-flop, flip-flop B in our example, than at the source, flip-flop A. Think about it. The clock edge at B is pushed later in time. This actually gives the data traveling from A more time to arrive and get stable before that later clock edge hits B.
Ah, so positive skew helps with setup time, gives it more margin.
It can improve your setup time margin, yes. Gives you more setup slack, which we'll get to, but there's a catch. Because the clock at B is later, the window for the next piece of data might be tighter, which can increase the risk of a hold time violation down the line if you're not careful.
Okay, so it helps one thing, potentially hurts another. What about the opposite, negative skew?
Right, negative skew is when the clock arrives earlier at the destination flip-flop B than at the source A. The clock edge at B is pulled forward in time. This earlier clock edge means the data has less time to travel from A to B and be ready before the setup window closes at B. So negative skew makes setup time violations much more likely.
Less time for the data to arrive. That sounds bad for setup.
It is generally bad for setup time. However, because the clock at B is earlier relative to the data changing, it can sometimes help with hold time, making it easier for the data to remain stable long enough after that earlier edge.
Wow. So it's this constant trade-off. Positive skew helps setup, might hurt hold. Negative skew helps hold, likely hurts setup.
Exactly. Designers are constantly navigating this. It's a strategic balancing act, path by path, trying to meet both setup and hold requirements across the entire chip. It's dictated by the physics of the signals.
That's incredibly complex. Okay, so designers are almost strategically using these tiny delays. That actually leads perfectly into our next term. If skew is about the clock's arrival time being inconsistent, slack sounds like it might be about the data signal itself, right? Like, is the data making its deadlines? What's slack all about?
You're exactly right. Slack is precisely that measure. It's the difference, the margin, between when a signal needs to arrive at its deadline and when it actually arrives at some point inside the chip. Think of it as the timing buffer. Do you have extra time, or are you running late? It's the safety margin for the data signal's timing.
Okay, safety margin. So back to our flip-flops A and B. How does slack apply to that data moving between them?
Great question. So data leaves A, travels through maybe some logic gates along those interconnect wires, and heads towards B. All that takes time, introduces delay. For flip-flop B to capture that data correctly on its next clock cycle, the data has to arrive within those setup and hold windows we just talked about, relative to B's clock edge. Setup slack tells us how much earlier the data arrived at B than it absolutely needed to for setup. Hold slack tells us how much longer the data stayed stable at B than it strictly needed to after the clock edge for hold.
So it's quantifying that margin for both setup and hold.
Precisely. And to calculate it, you need two key pieces of information. First is the required time. This is the deadline. It's determined by the clock period itself and the specific setup or hold time requirement of the destination flip-flop, B in our case. It's the absolute latest the data can arrive for setup or the earliest it can change for hold.
The deadline set by the clock and the flip-flop.
Okay. Second is the arrival time. This is when the data actually gets there. It includes all the delays, the signal experience, leaving A going through logic, traveling along wires. And critically, it also factors in the clock skew between A and B.
Ah, so skew affects the arrival time calculation too?
Directly, it shifts the effective timing window. So the basic formulas are pretty simple once you have those two times. For setup slack, it's required time minus arrival time. You want this to be positive. Positive means the data arrived before the deadline.
Arrived early. Good.
Yep. And for hold slack, it's arrival time minus required time. You also want this to be positive. Positive means the data stayed stable longer than required after the clock edge.
Stayed stable longer. Also good. Okay, so we get these numbers. Positive, hopefully. What does that number actually tell a designer about the chip? Is bigger always better? What if it's negative?
Right, what does it mean? That's the crucial part. The slack value tells you directly if the chip can run reliably at the speed it's designed for. There are three main scenarios for slack. First, positive slack. This is generally what you want. It means you're meeting the timing requirements and you have some margin, some wiggle room.
Wiggle room sounds good.
It is, because real chips aren't perfect. There are tiny manufacturing differences, temperatures change, voltage might dip slightly. Positive slack acts as a buffer against all that real-world variability. It makes the chip robust.
Makes sense. Protection against the unexpected. What about the opposite?
Negative slack. That's the big red flag.
Right.
It means you have a timing violation. The design is not meeting its timing goals at the target speed.
A violation, so it just doesn't work.
Pretty much. For a setup violation, negative setup slack, the data isn't getting there fast enough. The chip likely won't function correctly at that speed. You'll get errors, glitches, maybe total failure. For a hold violation, negative hold slack, the data changes too soon after the clock. Again, the captured data is unreliable, leading to unpredictable behavior. Negative slack is a fundamental design flaw. It has to be fixed.
So negative slack is a definite showstopper, no question.
Absolutely. Requires redesign, maybe resizing gates, rerouting wires, changing logic, whatever it takes to eliminate that negative slack.
Okay. What about the third option? What if it's exactly 0?
Zero slack. This is precarious. Technically, it means the design meets the timing requirements exactly, right on the knife edge, no margin at all.
Right on the edge. That sounds risky.
It is very risky. In a perfect simulation, it works. But in the real world, with those manufacturing variations, temperature changes, voltage fluctuations we talked about, any tiny imperfection can push that zero slack into negative territory. So a chip designed with zero slack might work sometimes, or fail intermittently, or only work reliably if you run it slower than intended. It's generally unacceptable for mass production.
So aiming for some healthy positive slack is really the goal, not 0 and definitely not negative.
Exactly. You need that positive margin for robustness and yield. Too much positive slack might mean a path is over-designed and could perhaps be optimized for lower power or smaller area, but some positive slack is essential. Negative slack is simply failure.
Wow, okay. That's a really clear picture of slack. So we've looked at skew, the clock's consistency, and slack, the data's timing margin. How do they really work together? Because it sounds like managing skew must directly impact your slack and vice versa. How does dealing with one affect the other in terms of the chip's overall performance and, just working reliably?
They are completely intertwined. You absolutely cannot manage one without considering the other. Managing both skew and slack is, well, it's the core challenge of timing closure in VLSI design. They're fundamental to making sure these incredibly complex digital circuits function correctly and meet their performance targets. Think of it like tuning an engine. You need both the fuel delivery, data with slack, and the spark timing, clock with skew, to be perfect.
Right, they have to work in harmony.
Precisely. As we saw, clock skew directly changes the required time in your slack calculation. If the clock arrives later at the destination, positive skew, the required time for setup gets effectively pushed later, potentially increasing setup slack. But if the clock arrives earlier, negative skew, the required time for setup moves earlier, squeezing the time available and reducing setup slack, potentially making it negative.
So skew directly eats into or adds to your slack budget.
It does. And unmanaged skew can easily cause negative slack, leading to those timing violations. Especially hold violations can be very sensitive to skew. It's a ripple effect. And you have to remember the scale we're talking about. Modern chips, billions of transistors running at gigahertz speeds. Clock cycles are measured in picoseconds, trillionths of a second.
Trillions. It's hard to even imagine.
It really is. Engineers are literally fighting physics at this level. Tiny variations in manufacturing, maybe a wire is a few atoms wider here or narrower there. Temperature differences across the silicon die, slight voltage drops as signals travel. All these things can change delays, induce extra skew, and eat away at that precious slack margin.
So a design might look perfect on paper or in simulation, but fail in the real world because of these tiny variations.
That's a constant worry. That's why positive slack is so vital. It provides that buffer. And designers absolutely have to make trade-offs. Sometimes fixing a setup violation might involve adding logic or buffers that actually worsen a hold violation on the same path or nearby. Or maybe optimizing for speed increases power consumption. It's always a multivariable optimization problem.
So do they have strategies? Like, can they intentionally introduce a bit of skew if it helps overall?
Yes, sometimes they do what's called useful skew, where a small controlled amount of skew is deliberately introduced on certain paths to help meet setup timing, while carefully ensuring it doesn't create hold problems. But more commonly, the focus is on minimizing skew, especially global skew across the whole chip. They use sophisticated techniques like designing complex clock trees.
Clock trees, like branches.
Exactly like branches on a tree. It's an intricate network designed to distribute the clock signal from the central source to all the flip-flops across the chip, ensuring the path length, and thus the delay, is as equal as possible to every endpoint. They also use things like PLLs phase-locked loops and DLLs delay-locked loops. These are special circuits that can generate very precise clock signals, multiply frequencies, and actively compensate for variations to keep the clock stable and synchronized.
Wow. So there's a whole science just to delivering the clock signal reliably.
A massive part of the design effort, yes. And all of this managing skew, calculating slack, making these trade-offs relies heavily on specialized software tools, electronic design automation or EDA tools. You simply cannot do this manually for billions of transistors and timing paths. These tools simulate everything, perform static timing analysis, STA, to check every single path for setup and hold violations, identify negative slack, pinpoint the critical paths.
The bottlenecks.
Right, the bottlenecks. And they help engineers figure out how to fix them, maybe make this transistor bigger, add a buffer here, reroute that wire. It's this iterative process of design, analysis, and refinement. And getting this right is why your smartphone works, why servers can crunch data, why everything digital functions reliably. It's the hidden foundation.
What an amazing journey into this hidden world. It's really given me a new appreciation for what's going on inside these chips. We've seen the delicate dance of the clock signals, how tiny timing differences, skew can cause issues. And then we explored slack, that critical buffer, the safety margin that determines if the data gets where it needs to go on time every time, especially under real-world conditions. It truly highlights the incredible precision needed.
It really does, and it makes you think, doesn't it? As we keep shrinking transistors down, heading towards atomic scales, and pushing clock speeds higher and higher, maybe even into terahertz ranges, how much harder does managing this microscopic timing, this skew and slack, actually become? What incredibly clever tricks, maybe even entirely new ways of designing circuits beyond the standard synchronous clock approach, are engineers cooking up right now? It really makes you appreciate the sheer ingenuity and, frankly, the relentless effort that goes into every single device you use. It's unseen, but it's absolutely essential.